I usually add extra credit to like whatever it's kind of being done for. So this might be either homeworks, but it wouldn't be on lab. Or, oh, the extra credit from the labs that you guys did with the line drawings? Yeah, I just drew it on the labs. So some people have a score of over 100.
Okay, so is the score plus that 10? Or is it 10 already calculated?
It's the score plus 10 already. I mean, you add up the points on the bottom, you'll see that I took off X number of points and you still got a certain score, so I must have included the extra credit.
Okay.
Did I push the start button yet? Oh, good. Okay. So, extra credit assignment. And I'm going to be picky on it too, so you have to do well and try hard. Is name and draw 10 alkanes with, first criteria is they have to be less than 10 carbons long. They must contain 2 or more bromines, fluorines, iodines. I'll let you use chlorine, but don't use 2 chlorines because I've named all of those. And if you just use 2 chlorines, you won't get anything. And when I say they can't already be on the computer, I mean basically if you just go and click the button 10 times and write 10 of those down, I already have those named. That doesn't help me any at all. That doesn't give you guys anything. And then what I'll do is I'll use some of the molecules on the test. And one of them has to be at least a cyclo. That way we get a bunch of those starting on the computer too. And to get the extra credit though, you have to both draw a molecule that can exist, meaning don't draw something that has 5 or 6 bonds to some carbon, and you have to name it correctly. So, you know, if you draw this molecule and you name this 3-bromo butane, you get no credit for that. Why? Should be 2. Or if you draw something like this and you say that this is 2,2,2-trimethyl pentane, you get no credit for that either. Why? Yeah, there's 5 bonds on that little carbon here in the middle since it's got 5 groups attached to it. So make sure that you draw these molecules in such a way that, you got to be careful. You can't just do anything. You have to kind of think about it a little bit. And what we'll do is we'll extend this, and every new class of molecules we might have something like this with a bunch of criteria. And this way, future generations get the benefit of your creativity, and I don't have to come up with all of these. Although, I have to be honest, it's probably more work for me to grade your molecules and do that than it is to just make them up on my own. But I think it's beneficial for you guys, so we'll do that. So that's up to 10 points. So they have to be interesting molecules. They have to be challenging molecules. They have to be, I got to be honest, I'm not going to consider things like this terribly exciting if that's all you do, because that's too easy, right? But if you do something like this, at least the person has to remember alphabetically which way to name it, right? So try to make the molecules interesting and challenging too. Meaning, I will be, here, we'll put an F up here. This goes here. Must be interesting and challenging. Well, on the computer, I have basically named anything and everything that is 10 carbons and less with just methyl and ethyl and propyl type groups, meaning you've got to at least throw a bromine, a fluorine, or an iodine in there. I've named every molecule that has a single chlorine, and I think I've named every molecule, or at least a good chunk of them, that has at least 2 chlorines in it. Meaning, throw in some bromines, fluorines, and iodines, and then mix it up, and you should be okay. But if you look at the internet, those are the types of molecules that you've been practicing, and that I've named just about every variation of those I can. You should also point out one other thing. I noticed that because I'm using the same set of molecules for chemical reactions, that occasionally there's one in there that we haven't shown you how to name. For instance, something like this, you really haven't learned how to name, because the longest chain should be 1, 2, 3, 4, 5, 6, 7, and so that makes it a heptane. And then on that heptane, you certainly have a methyl group, right? And on that methyl group, you have a chlorine. And so that chlorine is really a side chain on the methyl. So occasionally, because I haven't gone through and changed how I organize things, you might come across some name like this is chloro, this is 3-chloromethyl heptane, where the 3 is telling me where the methyl group is attached, and the chloromethyl is telling me that I've got a chlorine on the methyl. I just want you to be aware of it. I won't put those on the tests, but I noticed that since I'm randomly generating the practice, that occasionally a few of those crop up, and not to worry or stress about it too much. I won't include those on an exam, but it's not hurtful to practice naming them anyway, just for fun. And at least you'll understand why you might be getting some of those wrong if they've got a side chain on a side chain. And that's because I'm using the same database for both naming the molecules and doing chemical reactions. And sometimes the chemical reactions can produce compounds that we wouldn't expect or you to be able to name necessarily. But it's not outrageously out there. Okay, getting to the main topic of reactions. This is going to be a major theme through the next 6 chapters. And so I want you to realize that I've given you a bunch of resources for that. First off, there's an entire handout that I gave you on the first day of class. It says Understanding Organic Chemistry Reactions. Then it says Spring of 2013. That's because I didn't change it from 2013 and I didn't update the date, so it's still good. Notice that that's about 15 pages of goodness, of which I would say the first looks like 5 pages, I guess actually the first 7 pages are just how to think about chemical reactions, how to organize chemical reactions. Some of it will make sense after we talk about it today. Some of it will be topics that we cover in the next 6 chapters. It's kind of all mixed together, because in the end you're going to have to know it all. I consider the most useful part of this starting on page 8, where it simply goes by type of compound and chapter and tells you what chemical compounds are in, or what reactions are in there. That is basically the study guide for reactions. That lists every type of reaction that I'll throw up on the board. It'll cover every reaction that we do in class, and it'll cover every reaction on the test. So if you can remember those 2 pages, if those 2 pages, that information, you can organize it in your brain and make sense of it, then you'll do just fine on the reactions. Now, the other thing is first semester when we did reactions, how many types of reactions did we have? 6, right? And this semester we're going to have a lot more reactions, which is both good and bad. The bad part about it is you're going to have to remember a lot more stuff. I'm not sure there is a good part of it. It's fun. The other thing is that because we only have carbon, hydrogen, oxygen, and nitrogen for the most part, that means that the types of reactions that occur are all very similar, which is good, because if you can learn the basics of it, then the rest of them kind of make sense. It's also kind of bad in that since we're only dealing with carbon, hydrogen, oxygen, and nitrogen, means that they all start to look alike after a while if you're not careful to kind of clue in on them. And so what we're going to do when we cover the chemical reactions is we'll go through them a number of times before the test. So for instance, we're going to learn the chapter 19 reactions. Then we're going to go and learn about naming in chapter 20, and then we'll do reactions in chapter 20. And then we'll pick a day where we say, okay, now that we've done chapter 19 by itself, and now that we've done chapter 20 by itself, what happens if we stick chapter 19 and 20 together? It gets more difficult. And so this is one of those topics that's kind of like naming. If you can get it down right away, then the same patterns persist, and the first three tests are all very similar to each other, and you can do very well on them. If you don't get it down now, it only gets worse because we just keep adding to the pile. And so, again, this class, at least the organic chemistry part, is very front-loaded. Master the stuff in chapter 19 and 20, and the next 4 chapters will be cake. Don't master it now, and it's going to be tough. So, again, work hard early. We'll play later on in the semester when it gets a lot easier. Okay, so there's a number of different ways to think about reactions. There's a number of different schemes to categorize them. You can sometimes categorize things as more than one type of reaction. Organic chemistry is kind of messy in that respect. And so I usually, when I teach it, pick the most logical way for me to think about it. But there are other ways to think about it. The other thing is that I'll usually draw an example using just words, because some people like to remember the words. I've had people, instead of memorizing the way the reactions work, they just memorize what happens in the reaction, like the words that describe it. And that's one way to think about it, if that's what works for you. I'll draw them using Lewis structures, and I'll draw them primarily using line drawings just because it's quick and simple. And you'll notice that all of the quizzes and all of the tests are generally line drawings. But if you don't like line drawings, if you really like Lewis structures for some reason, go ahead and take every line drawing and just redraw it as a Lewis structure. It's not that hard. And so, what works best for you may not be the way I teach it all the time, but you can always say, hey, Jay, can we have another example, say, using line drawings or something? Oh, Jess, good morning. How are you? Thought you could sneak in, huh? Good luck. Okay, so the first set of reactions that we're going to talk about can be categorized into 3 types of reactions. We're going to talk about substitution reactions. We're going to talk about elimination reactions. Oh boy. Is that how you spell elimination, or is there like another E in there? And addition reactions. Oops. Oh, computer, don't stop on me now. Wow, Jay's already crashed his computer this early. This is awesome. This bodes well for the day, students. Yeah, PowerPoint can bite me. I don't know, has anyone got anything interesting to say while we're rebooting? How did basketball go, Jasmine? No exciting stories about sliding off the road into ditches or anything fun like that?
Almost.
Almost? Okay, so we've got substitution. We've got elimination. And then we have addition. And the first thing we're going to learn is that substitution and elimination reactions primarily occur if I have carbon-carbon single bonds, whereas addition reactions occur for things with carbon-carbon double bonds and triple bonds. And so what that means is that we'll really be covering substitution and elimination reactions in chapter 19, and then in chapter 20, we'll come in and we'll finish off that third set of reactions, which are addition reactions. And so one of the things that you should be thinking of going ahead is that when we mix these together, whether you have carbon-carbon single bonds or double bonds in a molecule is going to tell you what set of reactions that you can kind of look at. There's also a number of other things that you can use to help you determine what type of reaction it is. We're going to talk at some point about the different types of reaction arrows. We're going to talk about oxidation and reduction reactions. We're going to talk about dehydration and hydrolysis reactions, which is adding and removing water. But for now, we're just going to look at the most basic reactions, and we're going to realize that they're kind of boring, meaning there's no additional information. And in fact, you know, if I had to pick kind of the most boring set of reactions to talk about, that's chapter 19. Because chapter 19 is also the most boring molecules, meaning they just have carbon-carbon single bonds and hydrogens. And so if you just got carbon-carbon single bonds and hydrogens, there's not a whole lot that you can actually do. So let's take a look at that first one, substitution. And what a substitution reaction is if you remember way back to first semester, they're kind of like DD reactions. Do you guys remember what DD stood for in chemistry? Double displacement reactions. And so sometimes if you can kind of link up that word substitution and that word double displacement, you know, you'll kind of have an advantage. Now, we're going to call them substitution reactions here to match up with what the book says. Otherwise, frankly, I like to call them double displacement reactions. And the way substitution reactions work is sort of like the way double displacement reactions work. We're going to swap parts of molecules. And if I say the reaction in words, what we're really going to do is we're going to take some compound that's an alkane. We can add a variety of different things, but for now we're going to say we're going to add X2. And this is where sometimes chemistry maybe is a little silly. This simply stands for any halogen. And so that could be chlorine, fluorine, bromine, or iodine. And if we react those together, we get what's called a haloalkane, or sometimes it's called an alkyl chloride, or alkyl halide, I should say, make it generic. Plus, we're going to get an acid. And if I put those in terms of molecules, I mean, there's a bunch of different ways. Acid basically means HX. And so already you can see that depending upon if we're just going to say words or we're just going to use some shorthand notation in there and talk about acids as HX and, you know, represent halogens as X's, then that's one way to think about it. We can also think about it in terms of generic or a mechanism. And the way that I like to think about it for a mechanism is we show the important parts of the molecule and we ignore the other parts of the molecule. So that stands for a generic alkane, and what R says is that this is basically any alkane group, meaning that the molecule could be just CH4, meaning there's nothing there. It could be something like this, where I'm not drawing 90% of it, I'm only drawing that one carbon, and I'm calling all the rest R. So a lot of times what I like to say R is simply the rest of the molecule. I should also point out, because these reactions are pretty generic, really, once you've mastered one or two examples, the only thing that changes is the size of the alkane. So if you can do this reaction for propane, then you can do the reaction for butane and for hexane and for any of the molecules. So the key is focus on what's changing in the molecule, ignore all the extraneous stuff that might be attached to that molecule. And then I'm going to react that with an HX. I'm sorry, I switched examples. We're going to react that with X. Now, if I'm kind of drawing some more detail in there, we know that because those X's are really chlorines, fluorines, bromines, and iodines, they've got all those lone pairs around. And then what happens is we break bonds to form radicals. And so what happens is this bond is broken. And the way that bond is broken, or at least one way that we can do it, is simply with UV light. So if we shine a bright enough light, meaning high enough energy or intensity on it, and really I guess I'm mixing up all my terms, we'll simply say if we shine something that has a short enough wavelength or a high enough energy on our sample, then we can break that bond. And so then what we get is we have our original molecule here, Oops, that's still an H. And then I've broken that molecule up. And so what this dot represents is that's a lone electron. And we call anything that has a lone electron like that a radical. And what do we know about electrons? Or what do we know about the octet rule, I should say? Maybe we'll even phrase it that way. Octet rule says we want to have 8 electrons around, right? So if I break that bond, how many electrons does each atom have around it? 7, right? And so these are highly reactive. They want to get 8 electrons because they want to gain an electron. And so what happens is one of two things. The uninteresting thing is if they find each other, meaning they just reform that bond, then absolutely nothing interesting happens. However, sometimes what happens is that this looks and says, oh, there's an electron there that I can pair up with. And this also says there's an electron in that bond that I can pair up with. And so I'm going to continue it on the next slide. Now, I should point out that if you run out of room on your paper, it's perfectly legitimate to draw an arrow down like this, or, you know, I've even seen some people, they'll draw an arrow like this. So they go to the next line on their paper. So however you want to draw it is up to you. I'll redraw what we had so that we can kind of see what's going on, meaning this is already drawn. Oops, keep wanting to go one step ahead. And so that's interacting with that's interacting with that electron. And so what ends up happening is that I get a bond to an X atom. We'll draw it this way, I guess. And I get a bond that is now H and X. And so here's my acid, and here's my haloalkane. And so what we really did, meaning I don't care if you recognize or understand the mechanism. It's sort of up to you. What you'll find is that every one of you, well, there's only 7 of you, maybe not every one of you will be unique, but everyone will come up with a different way to remember these. Some people will remember that an alkane plus a halogen goes to an acid plus an alkyl halide. That's one way to remember what happens in the reaction and probably to figure it out. Some people will also remember the mechanism and go, oh, I know that I break a carbon-hydrogen bond and that I have to break an XX bond, and I know what happens then, because they'll think about it in terms of free radicals. Some people will simply say, oh, it's a double displacement reaction or a substitution reaction. I just swap an X and an H, because that's all I really did, right? Is swap an X and an H. Meaning if I redraw this reaction and I skip some of the in-between steps, all I did was swap, right? Meaning I took the X atom and I put it on one molecule and I'm left with an HX. So I just swapped. So which way you want to think about all these is entirely up to you. The best understanding, I think, comes from the mechanisms, because that'll let you look at new reactions in light of, oh, well, I know what happens to the bonds in this reaction. The way it's going to happen in this other reaction is similar, meaning we're making and breaking bonds. I think the hardest way is to memorize the word reactions. But I've seen people do it that way, and they did just fine on the test. And I would say intermediate between there is if you can remember the words swap and substitution, then you'll be pretty good. Okay, so the other way we can always show these is with actual molecules. So for instance, if I drew this, I guess I'll go to a new page. You know, if I say that this is CH3, right, plus HCl, what I'm saying is that, plus Cl2, what I'm saying is that I'm going to swap a hydrogen and a chlorine, H and Cl, and I get CH3CH2Cl plus HCl. Or my preferential method of drawing it is if I take ethane and react it with chlorine, I get chloroethane plus HCl. So I like line drawings. You know, sometimes I draw the dash in there to show that the bonds are there, and sometimes I don't. It's not correct or incorrect. It's just a different way of showing it. And what it is I'm just not consistent, which is one of my bad traits in life. Now the nice thing is once you've mastered this reaction, it's not too hard to see what happens in the next case. For instance, what if I just change that to that? What happens? Meaning I go from ethane to propane. Yeah, I just look and I say, well, I've got a hydrogen there, that can swap, so I can make this molecule. Or, you're right, there's also that middle hydrogen that could swap, so I could make, oops, this molecule. So there's really three answers to this. Now technically I could put another HCl there, but we are not going to worry about balancing the chemical reactions for these for the most part, because they get difficult later on, especially the oxidation reduction reactions. Instead, we just want to show what all the possible products are. And so in this case, because I've got two different hydrogens that can swap, I make two different products. Does that make sense? That's where it starts to get a little bit difficult, is that you can make multiple products. I would say otherwise swapping's pretty easy, right? Now, one of those products is favored, so often more than one product is made. I should also point out that if you look and do enough organic chemistry, what you find is that almost no one does too much chemistry with just alkanes, because of this very reason that alkane reactions tend to produce many, many different products. Instead, what they'll do is they'll convert the alkane to either an alkene, or they'll convert it to like an alcohol or some other functional group where you can control where the reaction occurs on the molecule instead of it being basically any hydrogen on that molecule. So there's often more than one product to make, and so really and generally one is most stable. One product is more stable. Now, this is very complicated in that, for instance, if I use fluorine or chlorine, I might have, say, a 75-25 split between the two molecules. Or if I use bromine, it might be more like 99%, 1%. And so we can't figure out what percentages of each product is going to be made. We can simply say which one is most likely to be made, and that the other one probably is made to a small amount. And the rule for this is based on the stability of what's called the carbocation, or the carboion. And what that really says is that if I've got a molecule that looks like this, that's the least stable, and that if I keep adding R groups onto it, and depending upon how many R groups are stuck to that carbon, they get more and more stable as I add more and more R groups. So this is the most stable, and this is the least stable radical. And we have a special name for these. We call these primary, secondary, and tertiary. And we don't really have a name for just the CH3 one because it's the only example of it, so it's just called a methane radical. Technically it's not even methane. Or it's sometimes, I guess it's really probably called a methyl radical, because that's the only example of it. And so it kind of has its own name. And so what we can say is that if I compare this versus this from that previous problem, when I break that bond, I'm left with that radical, so that electron that's there, right? Meaning, if I take that original molecule like this, and I say that if I break that hydrogen bond, and I break that hydrogen bond, what's left behind is a single electron from that bond, right? One of the electrons goes with the hydrogens, one of the electrons goes to that molecule. And so if we're thinking about it in terms of free radicals, then the tertiary free radical is the most stable. And what that means is that it produces the most product. And so what we have to be able to do is go and look at our carbon atoms and say whether it's primary, secondary, or tertiary. So for instance, the one in the middle, is that primary, secondary, or tertiary? So I'm talking about this carbon atom right there. If I redraw that, that's just R, C, R, and then it's got a hydrogen, right? And then it's got the radical. See, I don't draw that hydrogen normally. So what does that make that? Primary, secondary, or tertiary? And if I draw the one at the end, that's got two hydrogens on it. And so that really looks like one R group, a hydrogen, and that. So primary, secondary, or tertiary? Primary. And so that means that the secondary one is more stable, so that's our favored product. So if we go back a slide, what we'd simply say is that this is our most favored product. And so when you do a reaction, in general, what I always ask for is write all the organic products and circle the most stable one. And that's just a general rule in this class. Now, I have to be honest, on the computer practice, I cannot circle a molecule yet. I'm going to work on that. That's one of my goals for this class, is to be able to circle the most stable molecule when you're given a choice. But for now, I can't do it. But it will list all the products, and you can circle the most stable one on your own. Jasmine, you had a question?
So, for the most stable, we just mean the atom has less, the least amount of hydrogen.
Well, that's what I was going to say. There's another way to rephrase this rule. Instead of saying the rule like it said here, which is with free radicals, we can simply say that the swap occurs at the carbon with the least hydrogens. So I don't know if you've been reading ahead or not, or you might remember from last year. Oh, that's a long time ago. But yeah, it's the one with the most hydrogens. There's a person that came up and said this. His name is Saitsef. Swap occurs at the carbon with the least number of hydrogens. We're going to learn another rule that, did I say most? Sorry. There's another rule that's most. And so what that's really saying is that if I have a molecule like this, I've got two hydrogens here, and I've got three hydrogens here, so this is most likely to occur. And so again, if I'm doing that with my chlorine, then I can get this product, and HCl. And that this is the most stable. And we can also say, you know, that's our secondary carbon and that's our primary. So what's more reactive, the ends of the chain or the middle of the chain? Turns out the middle of the chain is, right? Now, the thing that gets tough about these reactions is the more carbons there are in the reaction, the more products you can make. So for instance, if I have 4 carbons or 5 carbons, how many different products can I make? And here, we'll just switch it up for fun. We'll throw bromine in there. So which hydrogens on that molecule can swap? That one can swap, right? Now what about this hydrogen on that end? Yeah, it's the same. So we don't, I mean, we can draw it, right? We can say it happens, but it's going to produce the same thing. This hydrogen, what's the same as that one? Yeah, so we're not going to consider that. And then we've got that hydrogen. And so what that says is that I can make three products. I can either have the chlorine or bromine on the end. I can have the bromine on the second carbon in. I can have the bromine on the third carbon in. And then, of course, the other part of that is I make some HBr. And then which molecules are the most stable? Yeah, either of these in the middle are tied, right? Because they're both secondary. So in this case, we'd expect both of those products to be formed in about equal quantities, and that the third one would be formed in much less.
Why do you cross out those two?
Oh, because these would produce the same products as other ones. So for instance, if I draw bromine on the end, that's the same thing as if I draw bromine on this end. And so we only draw one of the two molecules. Does that make sense that there's some symmetry in these molecules so that some of the hydrogens are the same? Whether it's kind of like the naming. These are both bromopentane, right? And we need to put a 1 because it doesn't matter how I draw it, I would always count from the end that has the bromine on it, right? So those reactions are called MonoSubstitution. And that means we only have one swap. We can have PolySubstitution, but it occurs less frequently. I think I have an extra C in there. And it's complicated. So what that means is that we ignore it. Aw, don't even start on me, computer. I don't need another crash. This is Monday, but for those interested, that was Jay beating on his computer. Anyway, polysubstitution reactions are more complicated, and so, wow, it didn't really like that at all. Polysubstituted reactions are more complicated, so we're going to ignore them and pretend they don't occur, basically. Meaning, we know that they occur to a small extent, but we won't ever consider them in class. I'll draw one example of what I mean by polysubstitution just to illustrate it, but like I said, we'll never worry about those reactions in class. I don't even think, well, maybe as extra credit I'd add one. So here's an example of what we mean by polysubstitution. So if I just take this molecule plus, say, Cl2, and we're going to assume that two swaps occur. And so what that means is that I can add two chlorines to that molecule. So I could add two chlorines to the first carbon. I could add I could add two chlorines to the second carbon. Can I add two chlorines to the third carbon? No. But now I can add, say, one to the first one and one to the second one. And I can add one to the first one and one to the second one. And I think that's it for combinations. Oh, plus the HCl, of course. And so notice that there's 4 products for that. And the more carbons I get, the more and more products I get to where it just gets to be ridiculous. And on a test, if I even gave you a molecule that had more than 3 carbons, you'd have to come up with 5 or 10 answers. And that's just silly and redundant. And so we don't worry about polysubstitution at all. Okay, so do you guys feel okay with substitution so far? Okay, now what we can do is we can extend on substitution, meaning that there are many compounds that can be substituted. But the idea is that they're all the same reaction. So if you remember substitution reactions, then you've mastered these other 2 reactions before we even show them to you. If you want to think about all these reactions as being kind of different, then it's going to be more complicated. So the other things that we tend to substitute are acids. And so we'll substitute HX and water. And I'm going to draw water like this because that's how we break water apart usually. And so what we mean is that I can show this reaction plus, say, Cl2, in which case, I got something like this plus something like this plus HCl, or I can show that very same reaction plus, say, water, in which case, what products can I get? Well, it's the exact same process, except instead of a chlorine, I'm going to swap on an OH group. So I get an OH group here. I can have an OH group in the middle. And instead of my product being HCl, since I'm swapping those, I actually may have my product be hydrogen gas because I'm pairing up two hydrogen atoms together. And we know that two hydrogen atoms paired together give us hydrogen gas. So it's up to you if you want to think about those as two different reactions, meaning whether I add chlorine or whether I add water is different, or you can simply say they're both substitutions. It doesn't matter. Alyssa.
Now here, does it matter if that one's a hoe and that one's a
No. Generally what happens when you're drawing HOs and O groups like that is that if you're drawing it on this end of the molecule, you draw it like this because it's really the oxygen connected to the carbon. And if you drew it on this end of the molecule, you draw it like that because it's the oxygen connected to the carbon. When we talk about, when we actually draw line structures and we want to make sure that it's obvious that there's a double bond there, and so that it's an O versus a HO or something like that, we'll draw it with a double bond explicitly shown. And so really, when we're drawing line drawings and Lewis structures, there's not really a difference between an O group, OH, and a HO group, HO. It's only when we're drawing those condensed formulas where, if you have CH3, CH2OH versus CH3, CHO, like this. So this is our O group, right? This is what we said is a HO group. And in this case, if I draw the line drawings, though, here I draw an OH. But if I drew it on the other end of the molecule, I draw it as HO. And here, if I really drew this is saying I have a double bond to an H. And so if I drew it on the other side, I draw it like that. And so for condensed structures, there's a difference between an O group and a HO group. But when you're drawing line drawings, there's no real difference between an O group and a HO group. And we just like saying those words, so we'll keep saying it over and over again. So the only time you really have to worry about it is condensed formulas. And I got to be honest, we don't use condensed formulas very much. If you're reading the book, they'll draw them a lot when they're talking about it in line, in which case you have to be careful and pay attention to it. But I draw things as pictures 99% of the time because pictures are less deceiving or easier to think about. Okay, so we had water that we can add, and then the idea is that it doesn't matter if I add, say, HCl. Notice that I'm still going to swap a chlorine and the hydrogens on that molecule. And I can, of course, swap a hydrogen and a hydrogen, but that doesn't change anything, does it? So we don't worry about it, in which case I get the same products. Except here, I get, as one of my products, still H2 gas. And so notice that the substitution, the swapping part is the same. We're always just going to swap a hydrogen and something on the other molecule. What changes sometimes is whether we're making, say, HCl or hydrogen gas. But that's just common sense, because if I'm making a hydrogen and a hydrogen stuck together, that makes hydrogen gas, right? But if I don't have an extra hydrogen over here, I must be making, say, like HCl. And so again, it doesn't matter what I'm substituting onto these compounds. The reaction mechanism is the same. So it doesn't matter whether it's an alcohol or a water, an acid, or a halogen atom. Okay, one last example, just to keep us honest. Here's what I mean by it doesn't really matter. Well, let's not make it too complicated. I forget. Sometimes I want to make these uber ugly and stuff because, you know, it doesn't really matter. But in this case, these reactions, the uglier the molecule gets, the uglier the reaction gets. Other reactions, what you'll see is that it doesn't matter what type the R group is. It doesn't matter how ugly the molecule makes. As long as it's got, say, like an OH group in the alcohol chapter, that's the only thing that reacts. So if I react that with, say, water, how many different molecules can I make, and which one is the most stable? I don't know. Seriously, off the top of my head, I can't tell you that it's 5 exactly. What I like to do is I like to go through and say which hydrogens can react. So for instance, this hydrogen can react, right? That hydrogen can react, right? This hydrogen can react, right? This one can react, and that one. So we're up to 5, right? What about this one right here? It's the same, right? So you guys remember when you're drawing isomers, you have to be careful that sometimes similar molecules look the same despite how you draw them. Well, that hydrogen's the exact same whether it's on this end of that methyl group or that end. Meaning, if I number my longest chain, I can either go 1, 2, 3, 4, 5, or I can start up here and go 1, 2, 3, 4, 5. It's the same. And so swapping that OH on that doesn't make a difference. And so really, I do only get 5 products. Can you see why line drawings are so nice? Could you imagine trying to draw Lewis structures for all of these? I'd shoot myself. And then, of course, I get H2 gas. And then I can stick an OH group here, stick an OH group here. I can stick an OH group here, stick an OH, oops, almost did that one twice. An OH group here. Oops, I went out of order. And an OH group here. That's not very systematic. Screw that, Jay. Start over. If we're going systematic, it should have been OH, 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 or HO. I just like HO groups better. I don't know. So I can have 5 different products for this one, depending upon where I stick that. So you can see how ugly this gets pretty quick, can't you? And then, which one's the most stable out of all those? Just this one. Because notice that that is a tertiary one, whereas these other ones are secondary, secondary, secondary. This is a primary, and that's a primary. So remember, the more carbons that's attached to it, the more stable it is. Or remember that this hydrogen is the most reactive because it's got the carbon that it's attached to has no other hydrogens, right? Remember, the hydrogen that's the least, or on the carbon with the least number of hydrogens is the one that's most likely to get substituted. And so you can kind of think about it both ways depending upon the rule. You can either think that tertiaries are the most stable, or you can think hydrogens on the carbon with the least hydrogen are most reactive. It kind of pairs up together, doesn't it? Okay, you guys feeling okay with substitution reactions? Okay, and the next one we're going to go to is the elimination. And sometimes, depending upon what these are called, they can be called dehydrogenation. Dehydrogenation. If it's specifically removing hydrogen gas, and it can be called a dehydration if we end up removing, say, a water molecule from something. And so depending upon what we're removing, it can be called a bunch of different things. But again, here the key is that the process is still the same for all these reactions, and what the actual products are will vary, and what people call it can vary. So if I'm thinking about this in terms of as generic as I can, so words, if I simply take an alkane and I heat it up to some specific temperature, I arbitrarily chose 500 K. Sometimes it just has a little symbol with the heat on it. Then I'm going to always make an alkene plus hydrogen gas. And so here's one of those things where, in order to tell it's a elimination reaction, you have to recognize what's on that reaction arrow, right? So if there's nothing on the arrow, we know it's a substitution, right? If there's something on the arrow, and that something is, in this case, heat, basically, we know it's going to be a elimination. The other thing is, if you look at substitutions to kind of compare, substitutions were like double displacement reactions in that you had to have two things reacting together, right? Elimination reactions are just one thing reacting, right? So you should be able to tell kind of by what's on the left side of the arrow whether you're going to do substitution or elimination. I got to be honest, if you try to do a substitution reaction with only one molecule, it's awful tough, isn't it? Now, you can do an elimination with two molecules. It just seems silly to me. Okay, so if we take a look at an alkane molecule, we can draw it like this. And what I'm emphasizing is that I've got two hydrogens like that, right? And what happens is we break those bonds. So we break adjacent hydrogen bonds, or carbon-hydrogen bonds. And so if we're thinking about this in terms of free radicals, what that leaves us is that I've got a free radical here and a free radical there, and then I've got a hydrogen with a free electron and that. So what I'm really saying is that when I break those bonds, remember that that produces an electron on each side of the bond that was broken, right? Because remember, bonds represent a shared electron. If I break, or shared pair of electrons, if I break that, each person gets one electron from that shared bond. Now what can happen, of course, is that they can go right back together and form just hydrogen or carbon-hydrogen bonds just like they can. Or what can happen is instead is that those two lone pairs can go together to form a double bond. And so I get something that looks like this, plus those hydrogen free radicals can form together to form a hydrogen gas like that. And so what we're really saying is that when we break things apart, if there's two different molecules that can be broken apart that can rearrange themselves, it's kind of like a substitution reaction. But if there's only one molecule and it breaks apart, or we cause these free radicals to form, then it almost has to react with itself and form a carbon-carbon double bond. So if I draw that, say, with a line drawing, and I'll pick the easiest one. What we're saying is that I've got a hydrogen here and a hydrogen here, and they're going to react together. And then my electrons, or my, actually, let me not show that way. Let me just show, I mean, on a test, all you're going to see is this to start with. You're just going to see that. It's not going to have any extra stuff drawn on it. What I want you to think about happening, so this is your mental picture, is that I've really got a bunch of hydrogens around, and that I break these bonds here so that I get something with electrons and then a couple of hydrogens with electrons. That these go to form a double bond, and so I get a molecule with a double bond and hydrogen gas. And then on the test, all you have to do is put this. Does that make sense? And so this is an intramolecular reaction, meaning it's between itself, as opposed to intermolecular, which is between two molecules. You guys with me? Yes, no? It's tough to tell. If we step it up a notch, meaning we really just add one more carbon, what can happen? Well, I've now got a bunch more hydrogens, right? And so the idea is that I can lose this hydrogen and that one, or I can lose that one and this one. But in both cases, that is the same as if I drew it like this, right? Those are the same. And so we don't draw it if it's the same like this. And so here we only get one product again, because the other one would be the same, right? So, you know, if you're off in the back of your head, you're going, well, I can also draw the double bond there, but that's the same. And if we ramp it up one more notch, then we start getting things where we can have multiple products, because here I've got lots of hydrogens, right? Meaning I can lose this set of hydrogens and make my double bond there. Or I can say, well, what if I lose the set that's in squares, in which case I get a double bond in the middle of the molecule, right? Or what if I tried to remove the ones that are in triangles? Yeah, that's a duplicate. Or sometimes we say it's redundant. So in this case, you get two products. And when we have more than one product, what do we know? One is most stable. Which one do you think is most stable, top or bottom? Yeah, this one. Zaitsev, remember, says that we lose hydrogens from the carbons with the least hydrogens. And so the two middle ones, there's only two hydrogens on each one, so we lose that one. So we remove the hydrogen from the carbon with the least number of hydrogens. And so we would favor this one. Okay, we're going to run a little late today. Remind me, and we'll just kind of finish early someday, or not worry about it or stress, or you know, you'll get the first Friday of every month off anyway, so there's advantages to it. What if I keep ramping it up? So we can ramp it up by mostly putting more carbons on things. Now you can ask me, Jay, how many molecules does that make? And I don't know off the top of my head. What I have to do is I go through and I say, okay, which hydrogens can react? Well, I've got a hydrogen on this carbon. I've got a hydrogen on this carbon, right? What do we know about the one up here? It's the same as the other one, right? I've got a hydrogen here. What about this carbon here? Yeah, there's no hydrogens because it's already got 4 bonds, right? And then I've got hydrogens here, but do these matter? They don't matter because there's no adjacent hydrogens. Remember, the hydrogens have to be next to each other for a carbon-carbon double bond to form. You can't form a double bond between two atoms that are really far apart. And so that one doesn't matter. So in the end, it looks like if I'm losing hydrogens, I can either lose that pair of hydrogens, or I can lose this pair of hydrogens as my options. And which one should be favored? Yeah, this one is the least number of hydrogens, so that's the one that's going to go first, right? And then this one is secondary. So here I've got a tertiary, a secondary, and a primary. And so I'm going to take the ones that have the least number of hydrogens, and so this is my most favored bisate Ceph. So we've got two things going on when we do these reactions. We have to identify what hydrogens react. We have to be careful not to count duplicates. And then after we've figured out which ones react, we have to also figure out kind of which ones are most likely to react to figure out our favored product. So we're going to break this down into lots of steps and practice it. And I know this isn't very soothing or doesn't make you feel good necessarily, but until you actually try this on your own, I could show you a million examples on the board, and you'll never know what part's going to get wrong on you. So you've got to practice it and then come and ask me questions. Jasmine. Okay, so this, well, so go from the beginning?
No, just like, okay, so I see.
Or ask which one is favored.
I see how you got the rows.
So the first thing I did is I ID'd hydrogens that can react, which means that I also removed duplicates. And so if I switch ink colors to kind of highlight that, that means that I said that this hydrogen can react, this one can react, and this one can react. And then I said that that hydrogen is a duplicate of the first hydrogen. And then we said that there's no hydrogens here, so those don't react. Right there, the big red dot. And then we said that even though there's hydrogens on the ends here, since they're not adjacent to another hydrogen, we can't remove them because we can only form carbon-carbon double bonds between adjacent atoms. You can't, for instance, go like this. You can't say, well, this has got a hydrogen, and this has got a hydrogen, oops, and go, oh, I'm going to make my double bond there. Because first off, is there even a single bond there? No. And the other thing is if you really want, we'll get the models out, and you can see that physically you just can't, necessarily wrap them around to do it. And so the hydrogens have to be adjacent. I want to do one more reaction. It's the exact same thing we've been talking about. It's just a variation, kind of like we could do before. And that's if I introduce, say, an HO on here, and I heat it up. Or we can think about it as the same thing as if I've got a chlorine here and I heat it up. It turns out that any atom, any other atom than hydrogen leaves first. And so what that's really saying is that if I'm breaking apart a bond, this is the bond that automatically gets broken. That the OH group or the chlorine group is automatically more reactive than a carbon-hydrogen bond. It turns out about the only thing less reactive than a carbon-hydrogen bond is a carbon-carbon bond. And so you'll notice that one of the things we've never done so far is break carbon-carbon bonds, right? Because they're not very reactive, especially the single bonds. And so what that's saying is that this will leave, and so that means the only two hydrogens that can react are the hydrogens that are adjacent to it. Or at least they're the ones that are like 99% more likely to leave than any other ones. And so that means that for each of these, what I'm going to do is I'm going to either make a double bond there or a double bond here. And in this case, I get water as my leaving group, HOH. We'll just write it that way since we like it. Or in this case, the molecule itself that we make is the same. And here our leaving group is HCl. And then, of course, the most favored one, if I have a choice, is this because there's 2 hydrogens versus 3. So this is secondary, this is primary, so this is most likely to leave. And it's the same thing for both ones. So what I'm trying to say is that sometimes you'll see an OH group or a chlorine on there, and it doesn't matter, or a bromine, or a fluorine, or an iodine, or anything else. It's the exact same process that we've been doing before, where we eliminate something from the molecule. What we eliminate in this case is just, instead of hydrogen gas, 2 adjacent hydrogens, we take whatever that group is plus an adjacent hydrogen. So again, same mechanism, just different atoms. Owen? Oh, I don't know why I circled the first one up there. I just, good, someone's paying attention. Brittany, was that your criticism too? I do that on purpose, folks, just to make sure you're paying attention. Nah, that's just Jay being silly. I have no idea why I circled that first one. I'd like to say that I was smart enough to plan ahead and circle the wrong thing so that you guys would be paying attention, but I'm not. So what if I have something, and see, the only way I can make these more difficult is I just add more and more atoms to it. What if I have that molecule? The process is still the same. So we know it's an elimination because we're either heating it, or you can just simply say there's only one molecule, so there's only one thing to do. And so I know I'm going to lose this OH group. So what hydrogens can react with that OH group? The ones that are adjacent, right? And on that carbon, it would be this one that's adjacent. So I've got 3 choices, right? So I can make 3 answers. And I just do it like this. The base part of the molecule never changes. We're not breaking any carbon-carbon bonds. The only question is, am I making the double bond there? Am I making the, oops, no, that's wrong. Am I making the double bond, let's be, so if I pick the first 2, it's here, here, or here. And of course I'm making plus H2O as my other part. So I'm either losing, you know, this set, or this set. So here's my circle, here's if I lose my square, here's if I lose the one in the triangle. And then I have to ask myself which one is the most stable. So which hydrogen is most likely to leave? And we want to choose the one that has the least number of hydrogens, right? And so what I'm saying is that if I look at this one, there's 3 hydrogens on that, right? There's 2 here, and there's only 1 on this one. So we should expect this one to be the one to most likely to leave. And that's kind of a lazy circle. It's an ugly circle. But that one is our most favored. I'm going to have to figure out how to show that on the computer, because that would be useful. I might just make it as a statement, like first is most stable, or second. I can do that probably if I think about it hard. That's my goal for the week, to figure out how to add that little piece to our practices. So I haven't put up a bunch of printable practice for the reactions yet, because I'm reformulating that. But I do have a bunch on the computer, and I certainly will have a bunch in the next day or 2. So that's reactions. 2 things, substitution or elimination. For now, that should hopefully be easy to tell which of the 2 you have to do, since you only have 2 choices. The hard part is getting used to figuring out which hydrogens are the ones that's going to react, right? And which one's the most stable. I should point out on the homework there's a 3rd type of reaction, but it's one that's from first semester. It's called combustion. If you forgot it, go look it up. And I'll cover it I'll answer questions on it in lab if you want. But we're over time considerably. I always forget we're starting 15 minutes early, so I think, oh yeah, 9 o'clock, no problem. We got till 9:30, right? No. Plus, how many of you have to run all the way across campus? And that is your own problem, if you haven't eaten already. Yeah, I'll be in my office.